We are now getting into chemical equilibrium. Pause the video and go ahead and read this section, continuing on to the next page as well, and fill in the blanks as you go through defining equilibrium. And as you go through defining equilibrium, think about reaction rates, because that's what we just finished calculating and learning about, is the rate of a reaction and how equilibrium is defined by that rate, a certain idea in the rate of reactions as you read this paragraph. So let's compare what we're familiar with, which is a reaction that goes to completion, where you're dealing with a limiting reactant, and oftentimes you're going to see a one-directional arrow. And in a reaction that goes to completion, you're going to see A react to form 2B, but until 2B, the formation of 2B stops when A runs out. So if you look at this, A is decreasing, and then it decreases until it hits a concentration of 0 as time passes. And that is when B also levels out and no longer increases. But notice how B is twice the rate of A in the end, just like the stoichiometry shows. We're going to see what happens in a reaction that is reversible, where you reach equilibrium, and of course to denote that we see a double arrow. So this is your equilibrium situation. And in that case, you're going to see A decrease with time and levels out. B is also going to increase twice as fast and also level out. And the leveling out between A and B is what we call equilibrium. So equilibrium occurs where they remain constant. The concentration remains constant over time. So I would call this the equilibrium point right here, where I see them maintaining to be constant over time. And so this part right here is where we've been studying. It's the kinetics part, where you're seeing changes in concentration over time. Equilibrium is what will happen eventually to any reversible reaction. So read this little story, the equilibrium story, fill in the blank, but also we're going to graph what we see here. So we're going to graph this equation between nitrogen and hydrogen, and we're going to sketch it according to what we see. So you'll notice in graph A, the reactants and products are not equal at equilibrium. So equilibrium occurs at this dotted line right here, and you'll notice how the concentrations are constant over time, unchanged over time, and so this is where equilibrium begins. Now, notice how they are not lined up or crisscross each other in any way. So equilibrium is not defined right here where they crisscross each other. It's defined when their concentrations are constant over time, and they don't have to be equal. They are not necessarily equal. Sometimes they can be, but that's not what defines equilibrium. All right, let's get into the equilibrium expression. So now that concentrations of reactants and products remain constant over time at equilibrium, we can actually, the fact that they're constant allows us to ratio the products over the reactants, raise them to their stoichiometric coefficients, and have a constant called the equilibrium expression and constant. Now, reminder, the little bracket is actually representing molar concentration, which is capital M, molarity. If you look at this general equation, you're seeing that in this generic reaction, you always take the products, which is C and D, concentration, and raise them to their stoichiometric coefficients, Y and Z, divided by, there's a division right here, so I'll make it very clear that it's a division that we should see. So this is divide. So this is divided by the reactants, which is A and B, raised to their stoichiometric coefficients. Make it really clear. And so K is, because these reactants and products are constant over time, we can ratio K and we can understand a lot about K from that. For instance, if K is greater than 1, that means at equilibrium there's more products than reactants. That's why a ratio can be a ratio where it's greater than 1. That's why it's high KEQ greater than 1. Now, if it's equal to 1, that means neither reactants nor products are favored. So both reactants and products, same number, and so it ends up being 1 in the end. Now, if the equilibrium is less than 1, that means that the reactants are favored. So it's favoring the left side, and that means more reactants than products. More reactants, which gives you a ratio that is less than 1, a lower number in the end. So let's go ahead and write the expression. So we're going to practice writing the expression, and then we're going to calculate KEQ constant as well. The expression is always products over reactants. So if you look in here, recall that the products that are solids and liquids do not count in the equilibrium because their concentration doesn't change much. So we treat them as though their concentration is 1 molarity. So we know that anytime we multiply or divide by 1, you always get the same number. So these two are your products. This is your product side. This is your reactant side. So we're going to do products over reactants. So I have to denote concentration, which is in brackets. So we start off with the products. So the product that counts would only be CaF2, so calcium fluoride. Water is a pure liquid. Pure liquids do not affect equilibrium. So the only product to count in this equilibrium expression is going to be calcium fluoride. And then we look at the reactants. This is a solid, so solids are not to count. And so the only one that we count is going to be the HF. So I'm going to actually mark off what we don't count. So this one we don't count, and this one we don't count in the end.
So the question is, why do solids not affect equilibrium? So right now, the system that you see in here, in this vessel, is at equilibrium. And you know it because you see that the 5 gas particles, or carbon dioxide molecules that you see floating around, stays at 5 over time. So in other words, it's 5 right now. 10 seconds later, it's still 5. So it's actually staying constant. The concentration of that carbon dioxide is staying constant over time. Now, you also notice some calcium oxide as well as calcium carbonate. That's in green. Calcium oxide is in orange. When I add, and by the way, this system's at equilibrium, and aside from the concentration, there's an error on this. There should be a double-headed arrow. So imagine the arrow going the other way as well, the reverse direction. As I add more calcium oxide, watch to see what happens. Does that change the amount of carbon dioxide? It's still 5, right? So it looks like adding more solid to a system that's at equilibrium has no impact on it. So if I add more or take away, you're going to see that it's not going to impact. Likewise, for calcium carbonate, which is also a solid, so these two are solids, you're going to see that it has no impact on the system. And you would see impact if you saw amounts of carbon dioxide changing. Adding more did not do anything. Notice adding more calcium carbonate didn't change the amount of carbon dioxide. So hopefully the takeaway is knowing that solids added to a system at equilibrium is not going to impact that impact that equilibrium system.
Now go ahead and finish the rest of these problems, making sure you do products over reactants and eliminate the pure liquids or pure solids and pure liquids. So make sure you eliminate them from the equilibrium expression. The answer key is right here so you can check your work as you go through it. So now we're going to calculate the K constant in this example problem. Here's our data chart with equilibrium concentrations of each of our substances in our reaction, and we're given those concentrations right here. Because we have equilibrium concentrations, we can substitute it into our equilibrium expression, and then we can calculate our KEQ constant from that. So let's write the expression first. Again, it's products over reactants raised to their stoichiometric coefficient. So looking at the reaction, all three of these substances, CO, CH4, and H2O, all have a coefficient of 1. Products are CH4 and H2O, so you write both of them raised to their first power because the stoichiometric coefficient is 1. And then of course the products or the reactants is CO and H2 raised to their corresponding stoichiometric coefficient. Notice H2 is 3 raised to the third power, just like it is in the equation. So now we can substitute those equilibrium concentrations depending on which experimental number we're asked to calculate it for. B is asking us to calculate experiment 1, so we substitute all those values and do the math and raise them to their corresponding stoichiometric coefficient, and we see it's 3.933. The same thing with experiment 2, and we notice that both experiment 1 and 2, when we substitute their equilibrium concentrations in to the expression, we see that the value is the same, which tells us that any experiment or wherever you reach equilibrium for the same reaction, as long as you're at the same temperature, is going to give you the same constant. And that same constant is what allows us to be able to use this equilibrium constant to calculate and understand equilibrium much more. Based on the equilibrium constant for experiment 1 and 2, is the reactant, product, or neither favored at equilibrium? So it looks like because our constant is greater than 1, it looks like we have more products than reactants. So we have this scenario for our KEQ to be greater than 1, which means there's more products, greater number of products than reactants at equilibrium. Okay, so pause the video. We're going to get into some stresses to a system that's at equilibrium. So we're going to understand, according to Shakyas Principle, what happens. So pause, read, fill in the blanks for all the major ideas that I'd like you to focus on in Shakyas Principle. Continue reading on the top over here, and it continues from the prior page, and we're going to get into Shakyas Principle and some stresses. And again, just a reminder that stresses are bad. You want to undo those stresses. So everything I'm going to talk about is going to be whatever the stress is, I'm going to do the opposite to undo that stress. So the equilibrium system is going to find a way to compensate for that stress. So let's go ahead and begin. The first stress is a stress on concentration. And so when you increase amounts of reactants or products for a system that is already at equilibrium, you're going to impact it in different ways. Let's see what specific stress will cause the reaction to either shift forward, shift reverse, or have no change. No change means there's no impact on the equilibrium system. So let's begin. If I add more N2, now N2 is on the reactant side of the equilibrium reaction. So adding more N2 would say, okay, we got to get rid of it. How do we get rid of N2? Well, we go forward, in the forward direction, very fast compared to the reverse. So the forward reaction is going really quickly, while the reverse is slower than the forward. And that will then get it back to equilibrium. And so, in other words, you are going to shift forward, as I stated, when you add N2. What would happen if you add N or O2? The same thing that happened when you added N2 will happen when you add O2 because it's on the same side of the it's on the same side, which is the reactant side. So you're going to see it find a way to try to consume that O2. How do you consume it? You go very fast forward. So you're going to be reacting these guys really quickly to form your products. And again, so it's going to be a forward shift until it reaches equilibrium again. What happens if you add NO2, which is the third separate scenario? So if you add NO2, so you're adding now the product, upon doing so, the reaction is going to want to reverse itself to go fast in the reverse direction to try to get rid of NO2. And to do so is to reverse it until it reaches equilibrium again. Every scenario is trying to get back to the equilibrium state. Now we look at the next stress. The next stress is an effect on pressure or volume. Remember that pressure and volume are inversely related. So if I increase the volume, it decreases the pressure, vice versa. Okay, so noticing the inverse relationship between pressure and volume. In the first scenario, there's two types of scenarios. One where there's actually unequal number of moles of gases. Now, what exerts pressure? Gases. And so because gases exert pressure, you have to count the moles of gases on the reactant side, and there's 4 total moles of gases on the reactant side and 2 moles of gases on the product side. So when you decrease volume, which means you're increasing pressure, now you've left less room. Now, if there's less room, what side do you think is going to favor? It's going to favor less moles of gases. So you're going to try to combine more moles of gases so that you can make less moles of gases. And to do so is to shift in the forward direction. The opposite would be the reverse direction. So if you've got more room now, volume wise, so there's more volume, thus less pressure, you're going to try to make more pressure. How do you make more pressure? You are going to, or make more moles of gases. Then you're going to shift to the reverse direction. What happens if they're equal? The moles of reactants and products are equal. And let's make sure we count that to see if they're equal. So here we have 2 moles of gases. And then here you see 2 moles of gases. So they are definitely, the moles of gases on the reactant side and product sides are equal. So with that, there's going to be no change. The reaction is not going to go faster in the forward direction, nor is it going to go faster in the reverse direction to compensate for the stress. So there's no change. Now we look at stresses on temperature. When there's a stress on temperature, what you're going to do is you're going to have to know whether the reaction is endothermic or exothermic. So once again, we're going to really stress the use of that triangle, and that triangle is going to represent our heat. So this triangle is the symbol for heat. And let's look at the first scenario. In the first scenario, your change in enthalpy is actually negative. So that negative means the reaction is exothermic, which means our heat is going to be positioned on the product side. And so if I increase temperature, as this specific stress states, I am going to find a way to try to absorb that energy, the heat, and the absorption is this way. In other words, it's exothermic going this way, left to right, but then endothermic going right to left. So you're going to try to absorb that heat, and absorb means endothermic, which is the reverse. So the reaction is going to reverse to try to compensate. and basically decrease the temperature, so it's absorbing that heat. If you have a decrease in temperature, well, what do you think the reaction is going to want to do? Of course, it's going to want to make heat. And to make heat means go to the exothermic direction, which is the forward direction. And that will make more heat to try to reach equilibrium again. What happens in the next scenario where you have an endothermic reaction? Once again, delta change in enthalpy is positive, so it is endothermic. And so we're going to put the triangle on the reactant side, anywhere on the reactant side. If you increase in temperature as the stress states here, you're going to want to absorb that heat. And so it's going to go endothermic, which means it's the forward direction. The reaction is going to move forward to try to reach equilibrium. And of course, the reverse, opposite. And so the last one is the catalyst. Adding a catalyst actually speeds the forward in the same manner as the reverse, so it's not going to affect the equilibrium in any particular way. So adding a catalyst has no change on the equilibrium. It might speed up the reaction, both the forward and the reverse, but it does not change or shift the equilibrium in any way. So let's look at some examples. All these are examples to practice. If you'd like to practice on your own, pause it and you can try it on your own, and then you can check with me as I talk through the answers. Okay. The first one, removing COCl2. So you're taking away this amount for the system that's at equilibrium. So notice the double arrow. So you're going to want to make more, right? Removing means you want to make more. How do you make more? Well, you shift forward to try to make more COCl2. That will increase the rate. So this is going to be a forward shift. B, you increase temperature. So if there's a temperature change, I'm always thinking I have to see if it's endothermic or exothermic. And it looks like it's exothermic because of the negative. The negative means we're dealing with an exothermic reaction. Now, what would happen if I increase the temperature? If I increase the temperature, I want to go and absorb that temperature. So it's going to go in the endothermic direction, which is the reverse direction. So endothermic is absorbing heat this way. So you're going this way. Whereas exothermic is going from left to right, and you're releasing heat. I don't want to further release heat because that's going to stress the system out further. So I'm going to absorb that heat, and that is the reverse shift. A decrease in volume means an increase in pressure, just always that inverse relationship. So I'm going to have to count my moles of gases. Anytime when I'm dealing with pressure, I would like to make sure I count my moles of gases. I see 1 mole of gas on the product, and I see 4 moles of gases on the reactant side. So if I increase pressure by decreasing volume, as stated right here, increase pressure by decreasing volume, I'm going to want to move to the side with less moles of gases because I have less room, and I've created more pressure. So if I move towards the reactant side, I'm creating more pressure because there's more moles of gases. So I'm going to move towards the products, which means I'm going to shift right, which means in the forward direction. I'm going to move in the forward direction where there's less moles of gases. For the next one, you're adding PBS. Now, of course, you're going to jump over and see that PBS is right here. And I know you're probably not noticing this, but you need to notice this. PBS is a solid. And what do we say about solids and their impact on equilibrium? They have none. So because this is a solid, you're going to see no change because solids have no impact on the system that's at equilibrium. I'd like to add this video on how pressure and volume changes systems that are at equilibrium. So this reaction is at equilibrium, and technically there should be a double-headed arrow right here, so there's a little bit of an error. If you count how many particles there are in this container, gas particles that is, you'll see 6 nitrogen dioxide molecules roaming about, and there should be 2 dinitrogen tetroxide molecules roaming about. So count it and you can see it from the modeling. I'm about to compress this container. When I compress this container, we're going to see less volume, less room for these particles to move. And so their equilibrium will find a way to shift in order to compensate for the less room that you have. And so let's look to see what the shift is. You'll notice that there are now more dinitrogen tetroxide. There's 2 more. And of course, there's 4 more is lost of the nitrogen dioxide. So there were 6 initially. 4 of them were taken away to make two of the dinitrogen tetroxide. And why that happens is because there's less room. Where there's less room, the equilibrium reaction is going to move towards the side with the less moles of gases, which is dinitrogen tetroxide. So for every 2 particle, you're going to be forming 1, and it's going to move quickly to form 1 so that it can compensate for the less room that you have inside this container. If I expand, you'll notice that the particles will go back to where it originally was, which is 6 particles of nitrogen dioxide and 2 particles of nitrogen tetroxide. When I compress, once again, you'll see the particles, 4 of the nitrogen dioxide decreasing to make 2 of the dinitrogen tetroxide. And we are reestablishing equilibrium, and how we know is as time passes, you'll see that the particles the amount of reactants and products remain constant over time. So let's go ahead and look at another different scenario, so another reaction. In the second reaction, you're going to see, once again, the error is the arrow, you're going to see 2 moles of you'll see the reactants, which is the yellow ones are the hydrogen diatomic molecule, purple are the iodines, and there's 2 hydrogens and 2 iodines. And of course, you also see some products, which is the Hi particle, gas particle, and there's it looks like there's 2 of them. So notice 2 of everything, 2 hydrogen, 2 iodine, and 2 hydrogen iodide particles as gases. Now I'm going to compress, and when I compress, you're going to see if there's any changes in the amounts of both hydrogen iodine and hydrogen iodide. So let's count. You see 2 hydrogen molecules, you still see 2 iodine molecules, and you still see 2 hydrogen iodide. Now, upon compressing, what you've done is you've changed the volume. Thus, you increase the pressure inside the system. But because there's 2 moles of gases on the reactant side and 2 moles of gases on the product side, you're not going to see this reaction try to compensate or the shift occur according to Le Chatelier, because they have the same number of moles of gas particles. So the reaction doesn't know where to go to try to compensate for equilibrium. So it looks like this whole reaction, this whole system is going to increase in pressure one way or another, and the reaction can't compensate for or will not shift forward nor reverse in order to try to reach equilibrium again. So all of this is continued practice on Le Chatelier's principle. Finishing up, I'm going to continue, I'm going to go a little faster. So this is an endothermic reaction, letter E, and endothermic because I see that delta H is positive, and so I know heat is on the reactant side. I'm going to squeeze it into this side here. If I increase temperature, I'm going to see that I'm going to shift to the side away from heat, or endothermic. So it's actually forward. Forward is my endothermic direction, away from heat. I go to F. In F, I'm increasing pressure, which means it's another way of saying I'm decreasing volume. So if I'm looking at volume and pressure, I'm adding moles of gases on the reactant side and the product side. I have 2 moles of gases here, and then I have 1 mole of gas on the product side. And an increase in pressure means I want to decrease the moles of gases. So I'm going to shift forward to try to decrease the pressure by going towards less moles of gases. For the next one, the same thing. So I'm going to count moles of gases, and it looks like I have 5 moles of gas here. Again, I have to look at the states of matter to make sure I see it. And I have 6 moles of gases here. So, and it looks like I'm decreasing pressure, so I want to try to increase pressure by moving forward towards the more moles of gases. Adding a catalyst, like we stated earlier, has no effect, so no change on the system that's at equilibrium. Once again, on example 2, we're seeing the same kind of problem, all le Chatier, heat on the reactant side because the enthalpy is positive. Change in enthalpy is positive. We're going to see all of these different changes that you see here. So the first one is a decrease in volume or increase in pressure. What would happen as a result? It looks like it's going to shift towards the side with less moles of gases. So I'm going to have to count my moles of gases. Once again, I see 2 moles of gases on the product side, and then I see 0 moles of gases on the reactant side. So in order to decrease pressure, I'm going to move towards the this direction, the reverse. Now, when it says right here, the effect on the quantity, what that means is if as a result of shifting this way, which means it's going faster towards the reactants, the quantity of NH3 is decreasing quite significantly. And so the effect is for NH3 is it's decreasing if it's shifting left. Decrease in temperature, I wanted to try to find a way to increase the heat, so I am going to go towards the exothermic direction, which is the left, towards heat, making more heat. And what it does to the amount of ammonium chloride, which is on that same side, so ammonium chloride is where heat is, and so it's going to increase my ammonia amount. Adding more NH3, in order to undo that change, I'm going to have to remove NH3. So the only way to remove NH3 is to shift it towards the left. So I'm shifting it this way towards the left. And that will have an impact on the amount of hydrogen chloride by decreasing it. So it's actually going to decrease the hydrogen chloride because it's going to be shifting towards making more ammonium chloride solid. Now removing ammonium chloride. Once again, I'm always going to notice to see what state of matter. It's a solid, so there's going to be no change. No change. If there's no change on that system, you're going to see the amount, the quantity for HCl compared to original is not going to be there's no change as well, because the reaction is not favoring or not going faster the forward or nor reverse. Removing HCl. If I remove HCl, removing this, I want to make more of it. because I want to undo this change, this stress. So how do I make more? Well, I go towards it. So it would be moving towards this way. And in doing so, because ammonium chloride is in the reactant side here, we're going to see that the amount of ammonium chloride is going to decrease with time as I move away. So it's decreasing to form these two substances quickly until it reaches equilibrium again. All right, for the third question, it's asking us how will the K constant change with each stress on the following reaction. So we're looking what changes K. And honestly, the only thing that changes K are things that are temperature related. So there's going to be no change for this one. No change here. And I'm going to abbreviate it NC, 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 and NC. The only thing that changes is temperature. So KEQ is temperature dependent. And because it's temperature dependent, that's the only thing that will change. So in order to know how KEQ will change is to understand whether it's an endothermic or exothermic. And from the looks of it, it looks like it's an exothermic in the forward direction because I see heat right here. So an increase in temperature. If you increase temperature, according to Le Chatelier, you're going to try to absorb that heat, which means the reaction is going to shift reverse. If you're shifting reverse, according to the KEQ, which is products over reactants, if you're shifting reverse, that means you're making more. If you're shifting this way, you're making more reactants. So you're making more reactants, and of course you're losing products. So what is this ratio going to look like as a result of this? So you're going to divide it into a larger number, and of course there's less to divide, so it's going to be even a bigger KEQ. So KEQ is actually going to be increasing in the end. So the key is that the reactants are increasing, and of course products are decreasing as a result. And there's much more reactants than products.